Hello, good afternoon, everyone. So welcome to 2025 Spring Physics Colloquium Series. My name is Ki-Young Kim, and I had the pleasure of organizing this Colloquium Series alongside Brian Clark for the past year or half. And as this marks the final semester in this role, and then we are excited to present a fantastic lineup of this colloquium speakers. We worked hard to bring in outstanding colloquium speakers, and also covering a broad range of physics disciplines in physics, and the many selections were based on your suggestions and recommendations. And thank you for your valuable input. And then also, we always welcome your new ideas, and then we also encourage you to continue doing this. All right, so now it's my pleasure to introduce today's colloquium speaker, Professor Carlos Romero-Talamás from UMBC. So Professor Romero-Talamás has had an impressive academic and a research journey spanning multiple disciplines and institutions. He earned his bachelor's science degree in engineering physics from the Monterrey Institute of Technology and Higher Education in Mexico, and followed by a Master of Space Studies from the International Space University in Strasbourg in France. And he then went to complete his PhD in mechanical engineering with a minor in physics, minor applied physics at Caltech in 2005. After his PhD, Professor Romero-Talamás joined the Lawrence Livermore National Laboratory as postdoc, and where he worked on the sustained spiral plasma experiment. And in 2008, he moved to IREAP here at the University of Maryland as a research scientist, working on high temperature plasma confinement in the Maryland Centrifugal Experiment. And also he investigated the atmospheric plasmas generated by lasers and the terahertz radiation. Since 2013, Professor Romero-Talamás has been a faculty member at the University of Maryland, Baltimore County, where he is currently an associate professor in mechanical engineering. In addition to his research, he has taken on several leadership roles, including serving as a graduate program director, and his work has been widely recognized, earning him several prestigious awards, including the DARPA Young Faculty Award in 2014 for his research on alternate fusion concepts, and also the University System of Maryland's Promise AGEP Outstanding Faculty Mentor Award in 2015, and most recently, Mid-Career Faculty Excellence Award from UMBC in 2023. And currently, Professor Romero-Talamás is leading the Centrifugal Mirror Fusion Experiment that he'll be talking today. And also, he's the CEO of Terra Fusion Energy Corporation, a startup company focusing on advancing fusion energy science technologies toward the practical applications. So today, he will share insight into his groundbreaking work on plasma confinement and then fusion research, energy research. Please join me welcoming Professor Romero-Talamás.
Well, thank you, Professor Kim, for the kind introduction, and thank you everyone for having me here today. I guess part of the bio should also mention that I'm a visiting professor in IREAP, so I actually spend more time here than at UMBC sometimes, actually most of the time. And so that's what I'm going to talk to you about, the experiment that we have here in IREAP, Building 223. Before I proceed, I would like to thank fellow professors and collaborators and many students that are now there or have been there and have helped or are helping achieve the results that we have, not just with hardware, but also with simulation and calculations. So first, why are we doing here? Why are we doing this? What's the motivation? And we know, hopefully everyone here now agrees that we are putting an unsustainable amount of greenhouse gases into the atmosphere. And that's because most of the energy sources by far are carbon-based and produce carbon dioxide and other greenhouse gases. It is, of course, urgent to decarbonize the economy, and we need all options on the table as fast as possible, of course. And there's a lot of technologies that are under development. This is from the Energy Information Administration, and there's been a lot of progress, so it's very encouraging, but it's not enough. We still have a lot of work to do. There's some technologies that are on the market. That doesn't mean that are deployed everywhere. There are some that are under development, and they take a lot of investment. And then there are some non-technological measures, change in attitudes, et cetera, that could also help. But overall, we have a long road to get there, to get to net zero, and even perhaps reverse the damage that we've made and the changes that we've made. And so fusion energy has been considered the holy grail or the ultimate source of energy for many of its advantages. But first, what is fusion energy? And so it's a combination of relatively light or light nuclei. It's a nuclear process whereby you combine two light nuclei and get another one where there's a slight mass difference. In this case, deuterium and tritium, that is the easiest fusion reaction that we know of, and that's the one that we will use. And the little cartoon here shows that the mass that you start with is slightly different than the mass that you end up with before and after the reaction. And the difference in mass is the energy that you get, and it comes from the binding energy using Einstein's famous equation. But it turns out that the energy density is very high. Excuse me. And so it has many advantages. First, that deuterium is abundant everywhere, so the fuel is abundant everywhere. Tritium is not naturally occurring, but it can be bred from lithium, which itself is abundant everywhere. Of course, once we get it to work, won't be dependent on seasonal variations, the weather, et cetera. There are no greenhouse gases emitted from it. The deuterium and tritium reaction yields energy and an alpha particle and a neutron. The neutron is used to transmutate the lithium, and the alpha particle can be vented to the atmosphere or captured for other uses. The irony is that we will produce so little helium that it may not be worthwhile capturing it. There's no risk of a runaway reaction. Unlike fission, if you put too much fuel, you quench the reaction. If you put too little fuel, it just fizzles out. There's no high-level nuclear waste, so you don't have to store radioactive waste for thousands of years or invest a lot of energy and infrastructure to transmutate it. The waste that is generated is relatively short-lived, and it's very weapons proliferation resistant. It's not proliferation proof, but it's resistant, meaning you can monitor it, you can inspect the sites where you will have fusion, and it will be very easy to detect if someone has modified the system for a nefarious purpose. But of course, you say, well, if it's so good, why do we not have it yet? In fact, the National Academy of Engineering considers achieving fusion energy, obtaining energy from fusion as one of the engineering grand challenges of our time because of all the benefits. But the problem it's been really hard to achieve. But before I get to those details, I like this cartoon, even though it's an imperfect cartoon, because it shows the enormous energy density that you can get from fusion energy. And in fact, the cartoon is incorrect because it doesn't show 2 million tons of coal or 21,000 rail cars of coal in comparison to a pickup truck with a couple of drums of deuterium and lithium. And so it almost sounds like science fiction, but the science of fusion is not the problem. It's the science of confinement of fusion. And so there are several ways that we can get there. The sun, of course, and all the stars that we know of work on fusion energy, and they do it with gravity. Of course, we don't know how to manipulate that here, but because the temperatures that you require are so high, you get to the plasma state, and then once you have a soup of charged particles floating around, you can use electric and magnetic fields to manipulate them. And so magnetic fields become a sort of pressure cooker to confine the plasma, so it's called magnetic confinement. And of course, you can also use inertial confinement, blast a little capsule with the deuterium and tritium fuel, create essentially a spherical rocket, compress it very quickly, and get to thermonuclear conditions that way as well. And so the ingredients to get to fusion energy, well, you want not just a few particles, but you want a large collection of particles. Of course, in order for the nuclei to get close enough, they have to be, that collection of particles has to have high energy, so the temperature has to be high. And that temperature turns out to be on the order of 100 million Kelvin. So, somewhat about 10 times hotter than the center of the sun. And unfortunately, not all the collisions are head-on collisions. Most of the collisions that happen in a plasma are scattering collisions. And so it takes many, many collisions before you get to head-on collisions. So then you have to have a confinement time. So before you can start to get enough energy out of fusion. So those three quantities are called the triple product. And there's a minimum, which is stated there, about 3 times 10 to the 21 kilo electron volt second per cubic meter. And that's called the Lawson criterion. And so the quest for fusion energy has been, how can we get there? And as we try to get there, we find that there are instabilities, there are leakage in our confinement system, and it's been a problem mostly of plasma physics more than nuclear physics. There's been many, many experiments, and in fact, this chart is not an exhaustive chart. I complained to Scott Hsu and Sam Bursell that they forgot to include the Maryland centrifugal experiment and now the centrifugal mirror experiment, which is what I'm going to talk about here today, is not on that chart. We still don't have temperature measurements of the machine that I'll show today, but we do have temperature measurements of the previous iteration, which was also in IREAP up to 2010. But all of these machines have achieved some level of success, and this is, of course, going toward the Lawson criterion, right? For a certain temperature, what density and confinement time, and tau, represented in the vertical axis, can you achieve? And of course, to get to net gain at the top right-hand corner of that plot, you have to be above Q of 1, where Q is the so-called amplification factor. But of course, not just demonstrate Q greater than 1. If you are serious about using fusion energy to power the planet, or at least to displace fossil fuels, then you have to be at Q of 5, 10, or more to make up for the losses in the equipment that is used to maintain the heating and to maintain the magnetic field, etc. That's called engineering Q. So this is just so-called scientific Q, where you're not taking into account the inefficiencies of the equipment that you use to get there. For example, the power supplies inefficiencies or laser inefficiencies, etc. The two main methods to get to fusion energy, magnetic confinement methods, are the tokamak and the stellarator. especially the tokamak, has been studied considerably for many decades and has been very successful in achieving the parameters. In fact, it's been very, very close to Q = 1 scientific. And there's now a company, there's actually more than one company, developing compact tokamaks, with very strong magnetic fields because of the advent of high temperature superconductors. And the stellarator as well. In fact, we have colleagues here at the University of Maryland that are studying how to optimize the magnetic field in a stellarator. Stellarators are very stable, but they require magnetic fields that are twisted, sort of like what you see there in those cartoons. And the tokamak, even if the magnetic fields are not, or at least the coils are not twisted, in both cases you require a lot of coils. And so it then becomes a problem of, even if it works, it's going to be very difficult, very expensive to maintain. So we're going to have to figure that out. But right now, we need to get there. We need to get to demonstrate that we can produce more energy than it consumes to get to the thermonuclear condition. And then we need to keep working to produce a lot more to make up for any losses in engineering. And then you need to produce even more, or at least avoid disruptions that may damage your equipment, so you don't have to spend all your time fixing your equipment and then actually make money. There's an alternative, and that's what we're working on here, and that's what's called a centrifugal mirror. Now, static mirrors, now of course they're simpler machines, and that's what makes the mirror attractive. You use less coils, it's a linear configuration, it's not a toroidal configuration. But the mirror by itself is not adequate to get to thermonuclear conditions. In other words, as soon as you start putting more and more energy to increase the temperature and the density to get to the thermonuclear conditions, you have instabilities that even in theory occur, and in practice it's been demonstrated, that the plasma essentially bulges out, you lose all your confinement, you have to start over, and you try many times and you never get there. But if you make the plasma rotate supersonically, then you can stabilize it, heat it, and increase the confinement both radially and axially along the axis of that cylinder that you see there. And so the principle of rotation is actually using the so-called E cross B drift, which is perhaps the most important drift, I will argue. If you take a plasma class, that's usually the first drift that you see. I have a little example here with a single particle. On a non-rotating mirror, that particle reflects back and forth from the regions of high magnetic field. That's an energy conservation principle. But if you add a radial electric field, or perpendicular to the magnetic field, then the particles start to rotate. You still have the axial motion, that back and forth, but for the same starting energy, at least in this example with the single particle, you get that this particle goes back and forth in a shorter path. And so that already gives you an indication that this is, of course, a single particle, right? It's not a large collection of particles, but that already gives you indication that this might be a better idea than the static mirror. Then you say, well, what if I put my single particle at different radii, and you notice that the angular velocity, again, starting with the same conditions, changes with respect to radius for some given electric field, and it's like, well, that starts to sound interesting. But of course, we need to make this a practical machine, and so how to impose that rotation in a actual machine, and it's very easy, actually, just put a center conductor. And in fact, in this cartoon, the conductor goes through the entire machine. In an actual machine, in the machine we have in building 223, we also have a conductor that goes through the entire machine, but you don't have to actually. As long as your magnetic flux surfaces are conductive enough, and that happens when the plasma is not even that hot, but hot enough such that the electrical conductivity is pretty good on any given flux surface. In this case here, on the innermost line that you see touching the electrode. As long as you have part of that conductor touching, the entire flux surface is charged to that potential, and then the electric field, propagates across the magnetic field and imposes the rotation. So again, engineering-wise, it's a very simple machine. And I'll argue, and I'll show that you don't require auxiliary heating or other forms of heating other that impose rotation, that current and voltage that you're putting in. So let's look to the simplest model, which is single fluid MHD. It's not the best model, but it's easy enough to follow. And in fact, for our machine, it's almost all you need. If you start with the momentum equation at the very top at the left, in steady state, then the radial currents balance collisional losses, and the azimuthal currents balance the thermal pressure. In fact, when you're rotating, the centrifugal force pushes flux out, and you can actually measure that change in flux with very simple loops outside the rotating plasma. But if you take only the components along the magnetic field, like it's done there at the lower left corner, if you dot it with B, and make a little variable change, some algebra, and then if you assume at the top right-hand side that the temperature is constant along a flux surface, and again, that's a decent assumption even at a fairly well below thermonuclear temperatures, but of course at thermonuclear temperatures is an excellent assumption. Then you can integrate that equation, you can separate it and integrate it straightforward, and you get that the ratio of density from the midplane, the bulge of your mirror, to the ends where you don't want it, so you want all your density to be between the strong magnets, goes as the Mach numbers, the exponential of the Mach number squared, times a factor that includes the mirror ratio, and the mirror ratio is the ratio of the maximum magnetic field to the minimum magnetic field. So you see that in that expression, in the solved expression where it's pressure at midplane and over pressure at the mirror ends, as long as you're supersonic and you have a decent mirror ratio, say of 10, you can have orders of magnitude higher pressure at the midplane than at the ends. And so why supersonic? And that's because interchange modes happen at the sound speed. So if you go supersonic, you can suppress them. And I'll show a plot a couple of slides down. But I want to show this. This was done by a former student of Professor Adil Hassam, who was now retired, of course, professor of physics here. And he was also a co-PI of the previous machine, and for a while, before he retired, of CMFX, of course, the machine we'll talk about today. Yiming Huang is now a researcher at the Princeton Plasma Physics Laboratory, but he did this for his PhD thesis here. And that essentially tells you how, once you start the rotation, at the left-hand side, the pressure, you'll accumulate most of the pressure right where you want it, where the highest pressure, the hottest plasma and density, are at the center of your mirror. But the angular velocity rotates, isorotates at any given flux surface. But between flux surfaces, you get a differential rotation or a sheared rotation. And that's important because that's exactly what helps stabilize and heat up the machine. And so if you take a profile radially across those colored plots, you get the line plots on the right-hand side in the slide. And so it was also Yiming Huang that did this simulations more than 20 years ago, where he assumed, he took a mid-plane slice in his simulation domain. He assumed a static mirror, put enough heat such that it went unstable and started a Rayleigh-Taylor-like instability, and so you get these striations that start to push the plasma outwards. And then he grabbed that last condition at suppose 10 time 101 in the numerical simulation, and then impose the rotation, and you're able to recover. You can see how the shear starts to destroy those striations, those two-dimensional bubbles, also called fluid instabilities, and eventually you can recover before your plasma escapes and leaves your rotating volume. But also, very importantly, is that shear helps heat the plasma through, even if the viscosity is very low, it helps add heat to the plasma. So it stabilizes it, it creates a deeper potential well from the centrifugal force that pushes the plasma towards the center, and it also adds heat from the rotation. That rotation also, of course, not just avoids these large interchange modes, but it also significantly suppresses transport, and I'll show some experimental evidence of that. Now, the model that Adil and others worked, the transport models, are as I'm showing here. And so we're still working in demonstrating that those are indeed the transport models. But the experimental evidence that we have so far indicates that overall the mirror works really well. The centrifugal mirror works really well. Now, this was the previous machine, the Maryland centrifugal experiment that was started around 2000, and it operated until about 2010. And the only reason it stopped operating is because DOE defunded it, not because it had reached the end of its life or we had done all we could. In fact, back then, we had proposed the next machine, and it took more than 10 years before we got the funding, which is the machine we have now to start building it. But very important, and it's not the first, by the way, it's not the first rotating magnetic mirror that has existed. There were many smaller machines before that. There were some in the Soviet Union, in Sweden, and in other places, smaller plasma experiments in laboratories. But at the time, MCX was the one that had the most power, that was running for the longest, etc. And so we did some interesting measurements back in the day. And for example, the velocity, we were able to show that it could go beyond a limit that's called the critical ionization velocity. That limit was proposed by Hans Alfvén back in his day. He was trying to explain planetary formation in the solar system, and he proposed to equate the ionization potential of matter to the rotation velocity across a magnetic field, and he got to a certain limit. So for example, for the ionization potential of hydrogen, you end up having a velocity of 50.9 kilometers per second. That is, in our mirror, if you look down here, if you take the velocity here and map it, since it's isorotating, map it to over here, that'll give you about 134.7 kilometers per second. 7 here is the mirror ratio, meaning the ratio of the strongest field here to the weakest field right here. Take the square root, that's done by looking at the same flux, excuse me, following the same flux, and so the area is smaller here than here, and that's where the square root comes from. You get 134.7 kilometers per second, and we showed back then it was a big problem. You know, many experiments before ours were not able to go beyond the CIV limit, and I like to think of the CIV limit as a sort of saturated mixture in a gas fluid mixture where you may be adding enthalpy, and the temperature and pressure may not change until you add enough enthalpy of, say, vaporization to then fully vaporize, in this case, fully ionize a plasma. And so if you have a resistive plasma, you have a lot of losses, but you may be stuck there in the rotation. And so we showed that at least for a brief moment, and I will direct your attention to the time scale at the top of those panels in half millisecond increments. Back in the day, that was a long time. That was many MHD times, many stability times. And so this was a pretty good achievement. In the center row, you see the angular velocity taken at two different places using ion Doppler spectroscopy. And between 4.5 and 5 milliseconds, the two curves overlap, which is what it should be. But then later, they don't overlap. And so there was an instability that occurred at about the same time. But we think that, so it could have been from differential rotation, meaning the flux surfaces were twisted. And then at some point, you start getting axial flows, which we saw in the high-speed camera. You will get this very impulsive release of plasma. But we think that that difference is caused mostly because the measurement was fixed, but the plasma and with the magnetic flux surfaces will migrate outwards because of the diamagnetic currents that are generated because of the centrifugal effect. And so, most importantly, at the bottom row, those panels indicate the temperature. So back then, we were able to show that you could get on the order of 100 eV electron volts or more, which was considered a very good temperature for an experiment of that type, of that size.
Can I ask a question?
Yes.
What's the electric and magnetic field strength?
Yes, thank you. For this machine, at the mirror throat was 2 Tesla, and at the center was about 0.25 Tesla.
And the electric field?
Oh, it was applied through a voltage at the center conductor of about 7 kilovolts. But as soon as the plasma will break down, the voltage will go down to 2 or 3 or maybe 4 kilovolts. It was not very high. Part of the issue with this machine was that we could not control the density. The plasma was overdense. It was very resistive. And that's why we stayed most of the time at the CIV limit, because we had a lot of radiative losses, charge exchange losses, and we just couldn't keep the energy high enough to heat it up and rotate it fast enough to keep high enough resistance across the magnetic field. In fact, in this experiment, the resistance across the magnetic flux surfaces, because the current has to propagate perpendicular to the magnetic field, it was about 4 ohms. And every time we went from 4 to 4.2, it was it's acceleration, right? Because that meant that the confinement was getting better. And I'll come back to that number when I talk about the next machine.
So 4 kilovolts with 2 Tesla produce 100 kilometers per second.
Oh, the 2 Tesla are at the mirror throats, where you see the necking of the flux surfaces in that diagram up there. That's where the 2 Tesla will be there. The 0.25 or so Tesla are at the midplane.
Okay, but I guess I'm just wondering whether that fast velocity that you're achieving is coming from that voltage that magnetic field that you're talking about.
Yes. An approximate way to get what the rotation is just by the magnitude of the E cross B drift is just the electric field over the magnetic field. That gives you a velocity in meters per second if you're using SI units. And you can approximate the electric field with the voltage over the distance that voltage drops. And so it's just V over A voltage over some distance A, which we know fairly well. There's maybe a little bit of error there, but 10, 20% perhaps error. And so you can get an average, radially average rotational velocity. But as you can see here, because this was measured using different chords with ion Doppler spectrometry, you have a parabolic profile, just like MHD theory predicts. And also, if you vary, just like in this slide, if you vary the ratio of the midplane magnetic field, or the mirror ratio, to the mirror magnetic field, then it predicts that as you lower the mirror ratio, confinement goes worse, and the density that you can hold goes down. And so this was published also many years ago, but it shows the basic functioning of the centrifugal mirror physics. And so, of course, this was very encouraging. And as I said, we had proposed the next machine. We wanted to have stronger fields. We wanted to have superconducting fields. And we said, we're very successful. And then at the time, DOE changed its policy and said, if you're not tokamak relevant, you're not getting the money. Then it took until ARPA-E came into 2020 and said, if you want to build another mirror machine, send the proposal and we'll review it. They did. They gave us the funding, and so it's a collaboration between UMBC and College Park, of course. And what we got was the Centrifugal Mirror Fusion Experiment. We started the design in 2020, and in 2022, we got first plasmas. We started with running it with a capacitor bank. But very importantly, we were able to build it with superconducting coils. Now, you may not recognize them, but these are used MRI magnets that we very carefully had to reverse engineer to make sure that they wouldn't break if we put them that close together. In fact, it took us about a year to figure out if we could put them that close. We wanted to put them even closer, get a stronger magnetic field between them, and eventually we realized we could probably break them because they're not made to have large amounts of force. Where the distance that they have right now is about 1.4 meters, and so they have about 22 kilonewtons force between them, and those 4 posts that you see are the ones that are holding those 22 kilonewtons, so about 2-ton force, 2 metric tons force between them, but that's within the shipping specification of the magnets, and so we kept it there. We wanted to move them a little bit closer. Instead of getting 0.35 Tesla, we wanted to get 0.5 Tesla, and we decided to be conservative and keep it within the shipping specifications. And so, because these are large bore, 90 centimeter MRI magnets, well, they're superconductors, they're very steady, they're great, but they have a long tube, right? Because they're meant for people to go into the tunnel. And so the flux surfaces that you see in that cutaway view end up being, the mirror ends up being stretched out very long. We don't actually need the mirror to be that long, but that's what we got. And it was much cheaper and much faster to use MRI magnets that came out of hospitals. In fact, one of them came out of the VA hospital. I went to see it before they took it out as they were dismantling it. The other one came from some hospital in New Mexico. And buying used MRI magnets is like buying a used car. You know, we had to contact several people, and some of them were like used car salesmen. Fortunately, we found one that you know, was honest enough, was not cheap, but was honest enough to help us and install it, from procuring the magnets, bringing them over, to installing the entire system, and then training us how to ramp them up and down. So we bought the power supplies for them as well. We, of course, before we got the vacuum chamber, we turned them on. The day we turned both of them on, we had turned them on separately to make sure they worked. The day we turned both of them on, we were very nervous. Every sound in the lab, every little creaking in the sound, you know, we were afraid that they were going to break on the inside, and then that was that. But they didn't, and they've held out very well. We set out a test stand with a magnetometer, with a Tesla meter, and the students spent a week measuring the magnetic field between them, and it's within, at the center, it's within 3% of what we had estimated. And towards the mirror, it's a little bit more than that, maybe 6%. But something that is fantastic about the centrifugal mirror is that you do not need high precision in the magnetic field to get it to work. Of course, more precise is better, but that small difference, in fact, we did simulations with misaligning the magnets to have a little bit of a crooked magnetic field, and it didn't really make a significant difference. So both magnets are within a few millimeters of each other, because we had a really hard time aligning them. We used a laser sight to try to align them, and we had to jack them up, shim them a little bit, then take them down, measure again. Eventually, we were satisfied with about 1.5 millimeters to 2 millimeters difference for one of them with respect to the other. Now, of course, we're still working on the diagnostics. We're installing ion Doppler spectroscopy, like you see in that circle with those lines, to have multiple views at different radial locations. We have many windows at the central cell, and unfortunately, we've run the machine for long enough that those windows are getting coated with metal vapor, and so we've had to replace a few of them. But by far, the simplest and the best diagnostic is the voltage and current measurement, which, it's actually, even though it's very high voltage that we're imposing on this machine, it's actually fairly easy to do. We're still working on Thomson scattering because that's considered the gold standard to get temperature and maybe density as well. I'll mention that the interferometer, we have an interferometer. The interferometer, it's a heterodyne type, 2-cord, 2-color interferometer. It works really well, but the windows are zinc selenide because it's a 10.6 micron CO2 laser that goes through zinc selenide windows. They're really good at absorbing some of the radiation coming out of the plasma. They heat up and they thermally expand by a little bit, and that expansion gets convolved with the density measurement. And it's very close to the density, so the equivalent phase shift from the thermal expansion is very close to the phase shift that you get from the density, because this machine, we learned how to control the density, but we operate at a lower density, and so it's very difficult for the interferometer to get above that thermal expansion of the windows, and so we're still working on that. Excuse me. But we have another way of estimating density. It's not over time, it's at a single time. It turns out that the centrifugal mirror makes for a very good capacitor. And so when it's rotating, it stores energy, again, just like a capacitor. And if you crowbar the discharge, it sends all that energy to ground. You can look at the RC time, at the time that it takes 1 e-volt to decay, and that turns out to be directly related to the momentum confinement time, that rotating momentum. And so we can, again, because we can measure the voltage and current in the machine, we can integrate that voltage times current, that power, over time, get a total energy stored right after the crowbar, excuse me, and equate it to a simple capacitor equation for energy stored. Now the volume, that's a guess. We're at this time we're guessing, so there's an error there, perhaps a factor of 2 or 3 on the actual volume. These are 0D estimates, if you will, of the plasma. And like I showed in a previous slide with the colors, the MHD slide, you have a radial and axial pressure profile. So it's not we model this as a hollow cylinder that rotates and it has uniform density and temperature everywhere. But in reality, it has a profile, right? That is not exactly that. So it's not a perfect analogy, but based on this, we get temperatures and densities on the order of 2 to 5 times 10 to the 18 per cubic meter. But that's, again, those are average densities. We think that the peak densities are around 10 to the 19 based on these profiles that we have. I'm also showing an example of one of the latest shots that we did, latest discharges that we did. This was at more than 60 kilovolts. Remember I mentioned that the previous machine, we had only run at, we will charge the capacitor bank at 7 kilovolts and immediately we'll go down to less than that. Well, here, we started using a capacitor bank for this machine, but then we told ARPA-E, hey, it's working really well, can you give us a little bit of money for a little bit more money for a DC power supply? And they said yes, so we bought a power supply that can go up to 100 kilovolts with about 100 kilowatts of power output. And so far we've gotten to around 60 to 65 kilovolts, which is where the theory says is the sweet spot for deuterium or DD plasmas. And that's what we've been using. We've been using deuterium. At the top panel, you see the voltage. There's a swing in the voltage because initially we have the machine at very high vacuum, and then we let the voltage go up a little bit, and then we puff gas. And when we puff gas, the voltage goes down and then takes some time to go back up. But also I want to direct your attention to the time axis. This is not milliseconds anymore. Now we're at seconds because we're putting less power, we have a less dense plasma, but we have a much more stable plasma. And so we're able to operate essentially indefinitely. We can operate for seconds, but we're limited by the heating of components that are not actively cooled. So that's the next step, to add active cooling of the electrodes so we can operate for much longer times. In this particular discharge, 2052, using the transport theory, the models that I showed earlier that were developed by Professor Adil Hassam and others, the estimate is that the temperature that we had is well, and also using neutrons, which I'll show in the next slide, neutron detection, half a keV with densities of about, again, volumetrically average densities of about 2 times 10 to the 18 per cubic meter. And in this case, a Mach number of 6 and an alpha in Mach number of about 0.4. Now, I didn't mention this, but we believe that the true limit of rotation is the alpha and Mach number. In other words, if you put too much density, the alpha and Mach number for a given magnetic field is going to go up, and at some point it's going to be so dense that even if you try to rotate it very fast, it's just going to go into interchange mode, and you're going to create a mess and not get to thermonuclear conditions. So we always try to stay below the alpha and Mach velocity of 1 or Mach number of 1. And since we don't have Thomson scattering, we do have neutron detectors. And in fact, just in December, we had a group of MIT students that came with their own neutron detectors. So we have 2 helium-3 detectors by the machine. And we're still making sure that they're calibrated. So we're still working through the calibration and making sure that what we're reading represents the actual neutron production. But the students brought 3 different types of detectors, and now we're cross-calibrating them with their detectors. They're much nicer than the ones we have, and in fact, those detectors are the ones that are going to be used in the Commonwealth Fusion System demonstration that hopefully will go online in 2027 or 2026, and then start producing significant amounts of 14 MeV neutrons, so DT neutrons, in much larger quantities than we have up in Devens, Massachusetts. And so it was exciting to have them here because, well, we have enough neutrons now produced from DD plasmas at the temperatures that we estimate here that they can be easily detected by different types of neutron detectors. In the upper right-hand corner, I show from that run, this is from the students, the 4 pi steroradian estimate of total neutron production on the order of 10 to the 7 neutrons per second, which is where we designed this machine to be. So what's exciting is that the machine is working as designed. At the lower right-hand corner, it's the estimate using Monte Carlo code calculation OpenMC for a given density and using the well-known reactivity equation for deuterium-deuterium fusion, how many counts per second we get at our detector, at the distance where it's at, with the efficiency, et cetera, or sensitivity that it has. And we come up with we detect typically 10 to the 2, 10 to the 3 neutrons per discharge per second. And for the densities that we estimate using the crowbar method, we arrive at temperatures, again, anywhere between 300 eV to almost a keV. And now, of course, if your density is lower, then your temperature is higher. If your density is higher, your temperature is lower, et cetera. So these are pressure curves So there's an uncertainty there, but there's a range loosely represented by that red ellipse where we know roughly the range of parameters that we're in. And so this became very encouraging because let me go back to this slide and remember how I mentioned that the resistance across the plasma is an indication of radial transport. Well, if you look at the resistance here, the voltage is in kilovolts, in this case 62.5 kilovolts, and the current is less than 0.4 amps. And so we have cross-field resistances of more than 150 kilo ohms for these shots that are, one of our best performing shots. And so that's something that is predicted by theory, but quite frankly, I was very skeptical that we will get to achieve it here, because I always thought that density will start to go up really fast and then we wouldn't be able to control it, but we learned how to control it, and now we can demonstrate that the cross-field resistance is very, very high, as the theory predicts, which means that the shear is also very high. And so, in spite of these beautiful results that we still have some work to do. We have no chairs or charge exchange measurement equipment, but we can do a quick estimate. The curve that you see there is the power curve that you will need depending on the voltage that you apply for a plasma that is, assume it's constant at 2 times 10 to the 18 and about 500 eV. Then for that given voltage, you get that curve, and it says that about 60 kilovolts is the bottom of the curve, the sweet spot. And if you look at the power there, is maybe 200-300 watts. But of course, for that particular shot, the one I showed in the previous slides, you get more like 12 kilowatts of power. And so the curve at the bottom was done assuming that you have the ionic charge state, or Z effective, as 1, because it's deuterium. You remove one electron and you're done. But in reality, we have impurities. Even though our vacuum is really good, we keep the machine very clean. When you put so much power to electrodes, you start to get impurities coming out. You get even tiny amounts of oxygen and nitrogen that seep in from the air. Maybe that they were there, they haven't finished coming out, etc. You get now more radiation out and more charge exchange, and now your effective charge state is higher than 1. So here we estimate that it's 2.5, and that's actually fairly high. And again, this is just based on this energy or power argument. But it also shows how dramatic it can be if you lower your level of impurities or your level of radiation. And the good news is that in an actual reactor, that is possible because the reactor itself is going to be very hot. So any water or whatever that you have there will essentially disappear. And in our machine, it may be possible, or rather in a reactor, that with this concept, it may be possible to have surfaces that are good getters, like liquid lithium, that has low vapor pressure, to absorb any extra hydrogen and impurities, including oxygen, and so to lower the amount of radiation that you have and lower the C effective. But it also is a matter of coating surfaces, for example, electrode surfaces, so they don't outgauss as much. Let me just finish with this slide where, because it's funded by ARPA-E, ARPA-E requires us to have a costing study. And in fact, they paid a different group to run the numbers for a reactor based on our concept. We assumed a certain scientific Q of 21, then based on all the balance of plant, et cetera, and then based on the cost of leasing the land and so on. The prediction was that we could have not so cheap for a first of a kind price, and this is called the levelized cost of electricity, using our concept based on the number of coils, the size of the machine, the equipment that will be required, the number of pumps, et cetera, assuming certain efficiency of the pumps. And the engineering Q could still be greater than 1, which of course is required. And so ARPA-E encouraged us and has been very supportive in spinning off a company that can help us search for funding to build an actual machine that could run with deuterium and tritium. And that's what we are doing now. And so, but we plan on building not a 100 megawatt system, but a centrifugal mirror can be scaled down to the so-called micro-reactor level. And that's important because, well, you need less money to build something small compared to, say, tokamaks that are limited by the size. Since they use auxiliary heating and many coils, the volume of tokamaks and stellarators is limited. And in terms of energy, because you use so much auxiliary heating, well, you better produce even more energy out. And so that gives you, and those auxiliary heating elements are not very efficient. And so that necessitates a machine of a minimum volume in order to make your investment worthwhile. The centrifugal mirror can be scaled down. There's also a minimum size, but it's much smaller than tokamaks, and so that allows us to ask for money. Still a lot for us, but not as much as we will have to ask if we were building a tokamak or a stellarator or perhaps some of the other machines. And so it's exciting, but it's still, you know, a high-risk investment if you want to invest. But I believe that we've made a lot of progress and that we will have a very interesting demonstration as soon as we can finish building the next machine. And I would like to acknowledge all of our collaborators and many people that have helped along the way with equipment, sometimes with advice, and perhaps even with help with the machine. Thank you.
Exciting talk. So do we have some questions for the speaker? Yeah.
Yes.
Actually, I have a lot.
Sure.
But can you start by just describing a little bit the scheme for extracting the energy? If you're actually producing power, where is the heat transfer occurring?
Sure.
Is it X-rays hitting something that's heating it up, or what's the actual energy transfer?
No, thank you. That's a very good question. So in this machine, like in many other machines, we'll use deuterium and tritium, which produces a neutron and an alpha particle. The neutron has 14.7 MeV, and the alpha particle has about 3 MeV. And the alpha particle, you know, will deposit some of its energy, not that much, at least according to theory. At best, perhaps 50%. So you use that to keep your plasma heated, but then you still have to get rid of that helium particle that eventually neutralizes, and you have to pump it out. But the neutrons go through your vessel, and then surrounding your machine, you want to have a breathing blanket, a shielding blanket that also serves as a cooling and a breathing blanket. And so we plan to use lead lithium. It's called 83% lead, 17% lithium, and that's a eutectic mixture that flows its liquid at low 200 Celsius or so, so fairly low temperature. And the lead, of course, helps slow down the neutrons, and the lithium, a combination of lithium-6 and lithium-7, helps capture the lithium-6, by the way, is what you want because it helps convert lithium into tritium, which you then can put back in. In the process of slowing down the neutron, then you get heat out of it. Now, lithium-7, which is actually the most abundant isotope of lithium, is an endothermic. It also generates tritium and an extra neutron, but it's endothermic. So you don't want too much of it because then you take up a lot of energy just making more tritium. But that's how you want to capture it, essentially by having a flow of liquid metal. And by the way, in the centrifugal mirror, because it's a simple linear machine, it's much easier to have flows that are aligned with the magnetic field, because you also have issues of drifts. They're called magnetofluid, of liquid metal flowing. If you try to flow across the magnetic field with a liquid metal, you may run into drift issues that increase the pressure that you have to have in your pumping system. And those are not trivial, right? Because you're going to be generating tritium, and you don't want your pumps to be simple pumps that with seals that may leak tritium. You want to capture it because it's radioactive, but also because it's highly valuable. So the system has to have permeation barriers, etc. But that's...
So there's a flow of liquid metal, it's absorbing neutron kinetic energy, and then the metal goes somewhere where it transfers to like a turbine?
Yes, the liquid metal goes through another cooling heat exchanger that vaporizes water, pressurizes it, and then, yeah, goes through a condenser, and that's the known part, you know. So we're replacing the heat source. Instead of using coal or gas, we're using fusion energy. Right. And of course, you could also use just the heat, because the liquid metal and the system can operate at a much higher temperature, unlike, say, fission power plants. We could potentially use that heat for process heating, not just to produce electricity, but for industrial processes that require high heat. And by the way, the liquid metal blanket is not the only one. You can also have lithium aluminate, for example, little beads of lithium aluminate that then when the neutrons capture that, they generate tritium and helium, it vaporizes, and then you move a lot of helium or a lot of gas through these beads. But then at some point you will have to replace those beads. Here you can keep adding lithium to the system and removing the tritium and helium that comes out of the transmutation.
Can I ask another quick one? What is the target temperature for when you're actually producing the right amount of fusion energy?
You mean in the plasma?
Yeah.
We'll be very happy if we can get to 10 keV. You know, the higher the better. And the rotating mirror, by the way, there's a group at Princeton, Professor Nat Fish and his students have been researching using the centrifugal mirror for proton-boron 11, which it's an aneutronic reaction, but that requires 400, 300 kilo electron volts. So in theory, the mirror can go very, very high in temperature, but we'll be very happy if we can be at 10 keV, 10 to 20 keV temperatures at a few times 10 to the 19, which is, by the way, low density compared to tokamaks, but we can get away with that because we don't use any other form of heating. Tokamaks have to operate, and accelerators have to operate at higher densities to get more power out, since the power goes as n squared, density squared. They have to operate at a much higher densities to get the return on the investment. And so, because we don't have that much investment of energy, we don't have to get that high return. So we can get away with lower densities, lower power densities. Yes?
What are the prospects for acquiring a bigger suite of plasma diagnostics so you can measure the spatial and temporal properties of the plasma?
We're just working on it. You know, it's not just having the funding, but finding the expertise, having the right components, and sometimes it's just waiting. You know, you order something and it's just waiting. But yes, we are working on getting more diagnostics. For example, colleagues at the Lawrence Livermore lab may bring their Thomson scattering here. We're building our own, but we may get a Thomson scattering system before then from colleagues at the Lawrence Livermore lab. And we're actually making measurements this week that will help on the amount of radiation at 532 nanometers, which is the laser that they have over there. And we'll let them know, and hopefully they can be here in a few weeks rather than years. But ARPA-E actually has been funding groups to develop diagnostics that can travel to different experiments with some success. They're not as compact and as easy to install and so on, but some of them have traveled, and so we've applied for that as well.
So it looks like your machine is running. I was wondering, I had two questions. One is, what are your next steps, or what are the first things that you want to show with it now on the physics front?
Sure.
My second one is, have you guys considered, like, there's all these auxiliary heating ways to put extra power into a plasma with ion cyclotron waves or electron resonance heating and things like that? Have you guys considered those type of extra heating?
Yeah, absolutely. We have, and in fact, RF heating may actually not work in our machine because of the density profile that we have. It may be possible. We've considered it. We had a collaboration at some point looking into it, but it's not clear that it will work. And if we don't need it, we want to avoid it as much as possible. Here, if you notice, the resistance across the plasma is more than 100 kiloohms easily. For this machine, we can run up to 100 kilovolts. For an actual reactor machine, again, or the so-called microreactor class, 5 megawatts or 1 megawatt, or up to 10 megawatt of power output, we will need megavolts. But you can sustain that level of voltage across your magnetic field because the resistance is so incredibly high. And so as long as you have such a high resistance, even with low currents, you can get ohmic heating. Now, if you compare that to tokamaks, where you can use the transformer effect to heat up the plasma by running currents along the magnetic field, well, you get a resistivity that goes as temperature to the -3/2, right? So the hotter it gets, the lower the resistivity or the higher the conductivity. And at some point, ohmic heating doesn't work. But in our machine, it actually gets better. As you add a higher voltage, you increase the resistance. Now the current may go down, but you still have a very large resistance, which means you're always adding heat to the machine. And so at least the models predict that we can get to thermonuclear conditions just by applying a high voltage. And of course, we're eager to test that. Yes, there's the option to have neutral beams, for example, that will work in our machine. But then you have to use valuable real estate from the blanket. You have to have holes and access to that. It becomes a much more expensive machine. And then instead of making it small, to make our investment worthwhile in energy, we'll have to now make it big. But if the theory that predicts, again, that you can get all the way to thermonuclear conditions just with an applied high voltage, and now it's not, megavolts is not chump change, but still, it's just one power input, very simple. If that works out, then there's no need for any other forms of auxiliary heating. There's other ways, by the way, that actually Professor Nat Fish has been investigating on adding a sort of rugosity, if you will, at the edges of the machine and creating a sort of wave heating just from the rotation. It's very, very interesting ways that we will love to test here, but there's only so much time and funding that we have for experiments.
Okay, just last question.
So, what did you actually do in the second machine compared to the first one to produce this improved performance? I'm asking because I'm not sure where the tokamaks, they make it bigger and bigger and bigger.
Yeah.
What do you do to get enhanced performance to go where you want to go? It's just not clear to me what you're doing.
Yeah, absolutely. We had that same question, what can we do to make it better? And so one was to control the neutral inventory. So we paid a lot of attention to the materials that we used to build the machine, to the cleanliness, so it's a much better vacuum condition that we have in the machine. And we have more pumping power too, so we can remove neutrals much better. And we puff gas rather than pre-fill the machine, which is what we used to do. And so because we were limited, the MCX, the previous machine, was very crude. We relied on essentially Paschen breakdown, or a form of Paschen breakdown across the magnetic field. So we had to have a minimum of neutral inventory to start the breakdown. And then we were not sure exactly how to limit the current. So we were putting kiloamps of current. Now we're putting less than an amp and only tens of kilowatts compared to kiloamps and megawatts of power to the previous machine. So the engineering essentially of the machine made a big difference. Keeping it clean, using aluminum for the chamber instead of stainless steel, so you can get to better vacuum if you use aluminum. Now we tried to coat the center conductor. That's actually the weakest link in all of the engineering. We had contacted a company to do tungsten plasma spray on the center conductor, and the company, they had done the limiter rings, which is the grounding. We also detached the rotating plasma. Instead of using the vessel as the ground, we use rings of thick copper that are coated with tungsten. And so they can survive the heat much better. And in fact, we haven't seen any tungsten in our spectroscopy lines. We see plenty of iron or suspected iron, but not tungsten. We tried to do that to the center conductor, which of course is stainless steel. And the manufacturer says, if we spray it, we're going to warp it. So we decided not to do it, and we're paying the price. But it was really on the engineering of materials. We also expanded the flux surfaces. I never understood why Adil wanted to put the insulators at the mirror throat where the power density is higher. He had some argument about alphane waves and so on that I never really understood. But this time around, we let the flux expand. And now the power density at the insulators is lower. So the plasma surface interactions are of lower power and therefore less material going back in. And also, because you're expanding the flux surfaces, they have to terminate at an insulator. And when the neutral density is lower there, you have less of a chance of arcing, so you can sustain a higher voltage between them. The more you expand them, the higher voltage you can sustain. And so it's a few of those improvements that have made a huge difference in the plasmas that we have. If we want to, we can put more gas and more power and run it like we used to run MCX. So we know how to go from where we are to much higher density, but then we will have to run for a lot shorter time or have more cooling, surfaces that can survive much higher power density. And so for now, we're happy demonstrating the stability of the machine, which was a big task for us at voltages and temperatures that are relevant to fusion. We're still within a fraction of where we want to be, but much higher than where we used to be.
All right, for those who have questions, you're welcome to come down to talk to the speakers. Okay, so thank you again, the speaker.
Yeah.
Okay.
Thank you.